A perfect ring of stars floats in the blackness of space, a galaxy shaped like a crescent moon. This is Hoag's object, a cosmic mystery that baffled astronomers for half a century. By the end of this story, you will understand the violent, forgotten collision that sculpted this celestial wonder. We will uncover how a smaller galaxy shot like a bullet through a larger one, and why the perpetrator of this cosmic crime is still missing. What does a perfectly symmetrical galaxy reveal about the chaotic forces shaping our universe? In 1950, astronomer Art Hoag was scanning photographic plates when he spotted something impossible. There, against the backdrop of the universe, was a perfect circle of blue stars, a brilliant halo surrounding a soft, yellow core. It looked more like a cosmic smoke ring or a planetary nebula than any known galaxy. But the light from this object had traveled for hundreds of millions of years to reach Earth, placing it far beyond our local stellar neighborhood. This was no nebula. It was an entire island universe, and its form defied every expectation. The ring was perfectly symmetrical and completely detached from the central core, floating in space with an eerie, unnatural precision. How could a galaxy, a system governed by gravity and chaos, achieve such perfect geometric order? The discovery sent a ripple of confusion through the astronomical community. Here was a celestial object that simply should not exist according to the prevailing understanding of galactic formation. Was it the result of a strange gravitational collapse, or was it the ghostly aftermath of a violent, unseen event? The mystery of Hoag's object was born in that moment of bewildering discovery, setting the stage for a half-century of speculation and debate. For decades, Hoag's object stood as a cosmic loner, a beautiful anomaly with no clear family. But it is not entirely alone. It belongs to an exclusive and peculiar class of structures known as ring galaxies. Think of a typical spiral galaxy, like our own Milky Way, with its arms winding out from a bright center in a graceful, continuous swirl. A ring galaxy shatters that familiar image. Its most prominent feature is a brilliant, circular band of young, blue stars, a stellar necklace that seems to float completely separate from the older, yellower core at its heart. This detached ring is the defining signature, a structure that looks more like a celestial bullseye than a spinning pinwheel. The formation of such a perfect geometric shape in the chaos of space demands a special kind of violence. While spiral galaxies form through the slow, steady collapse of gas clouds, ring galaxies are born from catastrophe. They are the cosmic equivalent of a stone dropped into a still pond where the ripples are made of stars. The most accepted theory points to a specific, devastating event, a galactic collision of a very particular kind. One galaxy, a smaller intruder, must plunge directly through the center of a larger, disc-shaped galaxy. This bullseye impact sends a powerful gravitational shockwave racing outward through the larger galaxy's disk. This wave compresses the vast clouds of gas and dust, triggering a firestorm of new star formation in a perfect, expanding circle. The result is that iconic ring, a luminous echo of a single, violent moment frozen in time. Hoag's object is the perfect, almost pure example of this phenomenon. Other ring galaxies, like the spectacular Cartwheel galaxy, show clearer signs of the recent trauma, with spokes of dust connecting the ring to the core. But in every case, the ring itself is a testament to a monumental disruption. Understanding this rare galactic class gives us our first major clue. The perfect circle of Hoag's object is not a symbol of calm and order, but the lingering scar from a forgotten cosmic crash. So where is the galaxy that caused it? The culprit seems to have vanished without a trace. the prevailing theory paints a picture of cosmic violence on an unimaginable scale. The perfect ring of Hoag's object is not a structure of calm creation, but the direct result of a head-on collision between two galaxies billions of years ago. Imagine the scene in slow motion. A smaller Intruder galaxy composed of billions of its own stars is on a perfect trajectory. It does not glance off the side of a larger, disc-shaped galaxy. Instead, it punches directly through the very center, a perfect bullseye impact. This is not a chaotic tangle or a slow merger. It is a single, piercing event, like a bullet passing through a spinning wheel. The gravitational forces unleashed by this direct hit are catastrophic. As the Intruder galaxy passes through the disk, its gravity acts like a stone dropped into a pond of stars and gas. It sends powerful shock waves, known as density waves, rippling outward through the larger galaxy's structure. These waves are not made of water, but of sheer gravitational force. They race through the galactic disk, compressing the vast clouds of hydrogen gas that float between the stars. Just as squeezing a handful of snow packs it into a hard ball of ice, this immense pressure triggers a firestorm of new star birth. The wavefront creates a circle of intense star formation, a stellar nursery that ignites into the brilliant blue ring we see today. Meanwhile, the older stars in the galaxy's central bulge are relatively unaffected, left behind as the yellow core. The Intruder galaxy, having delivered its transformative blow, simply continues on its way, escaping the scene of the crime with its momentum largely intact. This bullseye collision model provides a violent yet elegant solution. It explains the perfect symmetry of the ring, its detachment from the core, and the stark difference in the ages of the stars. The blue ring is young, a product of that single violent event. The yellow core is ancient, the surviving heart of the original galaxy. This theory turns the galaxy from a static portrait into a dynamic snapshot, a single frame frozen in time from a billion-year-old cosmic drama. But if this is the answer, it raises an even more compelling question. Where is the Intruder galaxy now? The galaxy's own stars tell the story of its violent past. When astronomers analyze the light from Hoag's object, they find two distinct populations of stars living in separate neighborhoods. The brilliant blue ring is a stellar nursery filled with young, hot stars that burn brightly and live fast. These are massive stellar infants, many of them only a few 100 million years old. Their intense blue light is the signature of recent, furious star formation, a firestorm ignited in the relatively recent cosmic past. Meanwhile, isolated in the center, the yellow core glows with the softer, warmer light of ancient stars. These are elderly suns, billions of years old, quietly burning through their fuel. They represent the original galactic core, the undisturbed heart of the larger galaxy that existed long before the catastrophic event. This stark division is the first major clue. If the entire structure had formed peacefully, we would expect to see a more mixed population of old and new stars spread throughout. The clear segregation points to a history of disruption, not calm evolution. The most telling detail of all is the vast, dark gap that separates the two. This is not a gentle fading but a clean, empty void between the core and the ring. It is a chasm that internal processes, like spontaneous star formation or gentle gravitational nudges, simply cannot create. Such a perfect, empty moat requires an immense external force to have swept through and cleared the area, pushing gas outward and leaving the central core behind. The ring's near-perfect circular symmetry seals the case. In nature, such geometric perfection almost always stems from a single, impulsive event. Think of the circular ripple from a raindrop hitting a pond, or the perfect ring of dust thrown up by an explosion. The symmetry of Hoag's object is that same kind of echo, but written on a galactic scale. The Intruder's direct bullseye impact sent a symmetrical shockwave through the disk, and the ring of young blue stars is the frozen record of that wave's leading edge. By reading the ages of these stars, astronomers can even estimate when the collision happened. The youth of the ring stars suggests the event occurred roughly 2 to 3 billion years ago, a specific moment in time when this galaxy's peaceful existence was violently and perfectly rewritten. So where is the Intruder galaxy now? This question has driven astronomers to scour the space around Hoag's object, searching for the perpetrator of this cosmic crime. Deep images reveal a tantalizing clue. A small, faint galaxy floats in the same region of space, close enough to be a potential suspect. Could this dim collection of stars be the bullet that pierced the larger galaxy billions of years ago? It is a compelling lead, but the evidence is circumstantial. The Intruder would have had to escape with just enough speed to flee the scene, yet remain gravitationally bound in the same general neighborhood. This faint galaxy might be that very culprit, now aged and dimmed, forever orbiting the beautiful structure it helped create. Yet another possibility is far more final. Perhaps the Intruder did not survive the collision. The gravitational forces involved in such a direct hit are titanic. It is possible the smaller galaxy was torn apart, its stars either absorbed into the ring or scattered into the dark halo surrounding Hoag's object. In this scenario, the Intruder sacrificed its own identity to sculpt this cosmic masterpiece, leaving no distinct remnant for us to find. Modern telescopes continue the hunt, not just for visible objects, but for the ghostly fingerprints of gravity itself. They search for subtle distortions in the light of background galaxies, hints of an invisible mass of dark matter that might be all that remains of the vanished Intruder. The absence of a clear culprit is in itself a profound piece of the puzzle. If we cannot find the other galaxy, does that disprove the collision theory, or does it simply mean the universe has done a perfect job of hiding the evidence? This ongoing search adds a layer of real-time detective work to a billion-year-old mystery, a reminder that some of the universe's greatest stories are still missing their most crucial characters. The most convincing evidence for this cosmic collision comes not from a telescope, but from a computer. Astrophysicists have recreated the proposed event inside powerful digital simulations, turning a theoretical idea into a visual spectacle. They begin with two virtual galaxies, setting their masses, speeds, and trajectories to mimic the conditions of deep space. The critical parameter is the angle of impact, a perfect bullseye shot straight through the center of the larger disk galaxy. When they run the simulation, the result is a gravitational ballet of pure chaos that resolves into stunning order. The Intruder galaxy pierces the disk, and in its wake, a powerful density wave ripples outward. You can watch this wave travel through the virtual galaxy like a ripple across a pond, except this ripple is made of sheer force. It sweeps up the diffuse gas and dust, compressing it into an ever-expanding, perfectly circular wall. And just as the theory predicts, this compressed wall of gas ignites, lighting up with the brilliant blue fire of newborn stars. The simulation doesn't just create a ring, it creates a ring that is detached from the central core, a ring that is stable for billions of years, and a ring that looks almost identical to the one we see in Hoag's object. This digital experimentation is more than just a pretty animation, it is a rigorous test. If the collision hypothesis were wrong, these simulations would fail to produce the ring structure, or it would quickly fall apart. Instead, they consistently generate a lasting, symmetrical ring, providing a powerful and compelling form of proof. We are essentially watching a playback of the crime, a recreation that strongly suggests we have identified not just the weapon, but the exact manner of the strike. The galaxy's motion tells its own story, a silent testimony written in the shifting light of its stars. To understand the forces that shaped Hoag's object, astronomers look beyond its beautiful form to its internal dynamics, a field known as kinematics. Using powerful spectrographs, they dissect the light from different parts of the ring and core, measuring the subtle red and blue shifts that reveal how fast the stars and gas are moving and in what direction. This is like learning to read the galaxy's hidden diary of motion. The data paints a clear and compelling picture. The brilliant ring of stars is not static. It is expanding outward, slowly but surely, like a ripple moving across a pond. This expansion pattern is the crucial piece of dynamical evidence. It is exactly what you would expect to see if a massive object had punched through the galactic center billions of years ago, sending a wave of energy rushing outwards. That wave pushed gas and dust ahead of it, and the ring of new stars formed in its wake, continuing to drift outward ever since. By measuring the speed of this expansion, astronomers can perform a kind of cosmic rewinding. They can calculate backwards to estimate when the ring began its journey, effectively dating the colossal collision that started it all. This kinematic analysis points to an event that occurred roughly 2 to 3 billion years in the past. It transforms our view of Hoag's object from a single, beautiful snapshot into a dynamic movie, allowing us to witness the ongoing aftermath of that ancient, violent encounter. The galaxy is not a frozen sculpture, but a living, breathing entity still feeling the echoes of a forgotten impact. This comparative approach turns the cosmos into a vast natural laboratory. Hoag's object is the most elegant member of a small but revealing family of ring galaxies, and by studying its cousins, we can see the shared blueprint of these cosmic accidents. The Cartwheel galaxy is a perfect example. Its ring is spectacular, but it is far from pristine. Thick, dusty spokes still visibly connect its outer ring to the central hub, like the lingering threads of a web that has not yet fully snapped. Nearby, two smaller companion galaxies are clearly visible, with one strongly suspected of being the intruder that recently smashed through the Cartwheel's disk. This system shows us a ring galaxy in its raw, youthful state, still bearing the fresh scars of its violent birth. Hoag's object, by contrast, appears serene and isolated. Its ring is perfectly detached, a clean circle with no connecting spokes, and its suspected intruder is faint and distant, if it is even the true culprit at all. So what do these differences tell us? They reveal the importance of time and the angle of impact. The Cartwheel's messy structure suggests a more recent collision, perhaps one that was not a perfect direct bullseye. Hoag's object, with its flawless symmetry and clear separation, points to an older, more precise event. It is the difference between witnessing a car crash moments after it happens, with debris still flying, and arriving hours later to find a single, perfectly skidded tire mark on the road. The passage of billions of years has allowed Hoag's ring to expand, the connecting material to dissipate, and the structure to settle into its current state of beautiful equilibrium. By placing Hoag's object alongside its more chaotic relatives, we can calibrate our understanding. The shared mechanism of a collisional density wave is confirmed, while the variations in their appearance help us pinpoint the specific conditions that make Hoag's object so uniquely perfect. This is not just about classifying one strange galaxy. It is about using these rare celestial formations to test our fundamental theories of how galaxies live, interact, and evolve across cosmic time. 2 to 3 billion years ago, a cataclysm rewrote this galaxy's story. This is not the ancient history of the universe, but a relatively recent event in cosmic terms. To understand the scale, consider that our own solar system had already been orbiting the Milky Way for billions of years by that point. Life on Earth was already ancient, with simple organisms flourishing in the oceans. While Earth was evolving slowly, this distant galaxy was undergoing a sudden, violent reinvention. The key to this timeline lies in the starlight itself. The brilliant blue stars populating the ring are not eternal. They are massive, hot, and short-lived, burning through their nuclear fuel in a few 100 million years. The fact that we see so many of them shining brightly today means their formation was a recent, explosive event. They are the living descendants of that initial shockwave, their youth pinpointing the moment of impact. This tells us the galaxy's core, with its ancient yellow stars, had existed peacefully for eons before its quiet life was abruptly interrupted. The original galaxy was likely a common spiral, a pinwheel of stars and gas spinning quietly through the void. Then, in a single, piercing moment, everything changed. The Intruder's bullseye strike transformed that familiar spiral into a celestial crescent, an event so rapid on a galactic timescale it was over in a flash. Piecing together this chronology turns a static image into a dramatic narrative. We can now visualize the sequence, from a calm spiral existence to a violent puncture, and the slow, beautiful expansion of the resulting ring. This timeline grounds the theory in a specific moment, a forgotten chapter in cosmic history when two galaxies met, and one was sculpted into a perfect, enduring ring. Yet the entire collision was guided by an invisible hand. The key player in this cosmic drama was not the brilliant stars or the colorful gas, but dark matter, the mysterious substance that forms the hidden scaffolding of every galaxy. Think of a galaxy not as a flat disk of stars, but as a sphere of invisible matter, with the visible stars and gas merely floating at its center. This immense, unseen halo of dark matter provides the vast majority of a galaxy's gravity, creating a deep gravitational well that holds everything together. When the Intruder galaxy shot through the heart of what would become Hoag's object, it was not just flying through a thin disk of stars, it was plunging through this powerful, invisible sphere of dark matter. This hidden halo acted like a cosmic steering mechanism, its immense gravity influencing the Intruder's precise path and speed, ensuring the collision was a clean, direct bullseye rather than a messy, disruptive sideswipe. More importantly, this dark matter is the reason the beautiful ring has not simply flown apart over the last 3 billion years. The gravitational pull from this invisible halo wraps around the entire structure, acting as a stabilizing cage. It keeps the expanding ring of stars tethered, preventing it from dissipating into the void like smoke in the wind. Without the constant, gentle embrace of dark matter's gravity, the ring would have lost its coherent shape eons ago, and we would see only a scattered, shapeless cloud of stars. This is why understanding dark matter is not an abstract exercise. It is essential for creating accurate computer models of the event. When scientists simulate the collision, they must include the gravitational influence of this invisible component, or the virtual ring will not form correctly or will quickly disintegrate. Dark matter was the silent director of this entire galactic performance, orchestrating the impact and ensuring its beautiful result would endure for billions of years, a permanent monument written in starlight and shaped by the unseen. That brilliant blue ring is a firestorm of new life, a stellar nursery born directly from violence. When the smaller galaxy punched through the center, it sent a colossal shockwave of gravitational force racing outward. Picture the immense clouds of hydrogen gas and cosmic dust that filled the galactic disk before the impact. They would diffuse and spread out like a thin, cold fog. The shockwave acted like an invisible cosmic plow, sweeping through this fog and pushing everything in its path into an ever-expanding wall. This wall of gas became incredibly dense and hot, a region of intense pressure. In such extreme conditions, the delicate balance within these clouds is shattered. The force of gravity, which had been gently tugging on the gas for eons, suddenly becomes overwhelming. The compressed gas can no longer resist its own weight, and it begins to collapse in on itself. These collapsing pockets are the seeds of new stars. Each one heats up under the immense pressure until nuclear fusion ignites in its core and a new sun is born. This is why the ring glows with such an intense, brilliant blue light. Blue stars are the most massive, hottest, and shortest-lived stars in the universe. Their fierce radiation floods the surrounding space, illuminating the very gas clouds that gave them life. This event completely reset the star-forming history of the galaxy's outer regions. Before the collision, that area was likely quiet, with star formation a slow and sporadic process. The impact turned it into a blazing, circular production line for new suns. It is a profound cosmic irony that destruction on such a scale can be the direct catalyst for creation. The ring of Hoag's object is not just a scar, it is a phoenix of stars rising from the ashes of a forgotten collision. This perfect symmetry is the ultimate clue to the nature of the collision. A ring of stars this flawlessly circular could not have formed from a gentle process or a random encounter. It is the direct result of a single, perfectly aimed event. Think of it like a stone dropped into a perfectly still pond. The resulting ripples are always perfect circles, expanding outward from the point of impact. Now imagine the stone is an entire galaxy, and the pond is the vast, flat disk of another. For Hoag's object, the Intruder galaxy had to strike the very center of the larger disk. Its trajectory was a cosmic bullseye, a direct hit on the galactic core. This precise alignment sent a symmetrical shockwave of gravitational force racing outward in all directions at once. This wave compressed the galaxy's gas into a uniform, circular wall, which then ignited into the ring of blue stars we see today. Had the impact been even slightly off-center, the result would have been a messy, lopsided oval or a broken, irregular structure. The ring's perfection is therefore a frozen record of that moment, a testament to the incredible precision of the ancient collision. It tells us that the Intruder's path was not a glancing blow, but a clean, surgical strike. This geometric purity is what makes Hoag's object so rare and so valuable. It is the universe's own demonstration of how chaos, when guided by a perfect set of conditions, can give rise to breathtaking order. Yet the elegance of the collision theory has not stopped scientists from exploring other possibilities. Could such a perfect structure have formed through a quieter, more internal process? One alternative suggests the galaxy once possessed a massive, unstable bar of stars cutting through its center. Such a bar can act like a giant gravitational engine, funneling gas and energy outward. In theory, this could potentially trigger star formation in a ring-like pattern. But this model runs into a critical issue: the clean, empty gap between the ring and the core. An internal bar would not so completely evacuate that vast region of space. It would likely leave behind a trail of stars or connecting structures. Another, more exotic idea proposes an accretion event, where the galaxy captured a massive stream of intergalactic gas from the cosmic void. As this fresh fuel fell onto the galaxy, it might have settled into a ring and ignited new stars. While intriguing, this scenario fails to explain the stark age difference between the ancient yellow core and the youthful blue ring. A gentle inflow of gas would not reset the star formation clock so dramatically in one specific area while leaving the core entirely untouched. The very weaknesses of these alternative ideas actually reinforce the collision model. They struggle to account for the complete package, the detached ring, the age disparity, and the perfect symmetry all at once. Investigating every avenue, even the less likely ones, is a cornerstone of good science. It forces researchers to stress test their favorite hypothesis, to ask the hard questions and ensure the answer they have is not just beautiful but truly bulletproof. In the case of Hoag's object, this rigorous process of elimination only makes the case for an ancient, violent encounter more compelling than ever. Our cosmic filing system struggles with a galaxy like this. Astronomers typically sort galaxies into neat categories, like organizing books on a shelf. You have the ellipticals, smooth and featureless spheres of ancient stars. You have the majestic spirals like our own Milky Way with their winding arms of dust and light. And you have the irregulars, the chaotic jumbles that defy any simple shape. Hoag's object fits none of these. It is not a sphere, it is not a pinwheel, and its perfection is the opposite of chaos. It defies the standard catalogue, forcing the creation of a new classification just for itself, the Hoag-type ring galaxy. This is not a minor subcategory, it is a class defined by a single, spectacular prototype. Its very existence is a challenge to our desire for orderly boxes. The universe is not a tidy library, it is a wild and inventive workshop, constantly creating forms we never anticipated. Every time we think we have the rules of galactic evolution figured out, a cosmic outlier like Hoag's object appears, a brilliant reminder that our classifications are merely human attempts to impose order on a cosmos brimming with creative anarchy. This galaxy is more than just a beautiful accident. It is a permanent monument to the universe's boundless diversity, a single object that expands our entire conception of what is possible. For the dedicated amateur astronomer, spotting Hoag's object is the ultimate test of skill and patience. This cosmic crescent hides within the constellation of serpents, the serpent, a faint and elusive smudge of light. You will not see its perfect ring or brilliant colors with your own eyes. That breathtaking image is built from hours of exposure through the world's most powerful telescopes. Through an eyepiece, even with a moderate-sized telescope under a truly dark sky, it reveals itself only as a subtle, ethereal glow. Its small apparent size and low surface brightness mean it blends almost perfectly with the black of space, a ghostly signature challenging you to find it. The first step is locating the right patch of sky. You must find your way to a specific point between the stars in Serpent's caput, the serpent's head. This is not a journey for a small scope in a light-polluted city. It demands a telescope of at least 8 inches in aperture, and ideally much larger, paired with a pristine, moonless night far from any urban glow. Using a detailed star chart or a computerized go-to system is essential to navigate to its precise coordinates. Once you believe you are pointed in the right direction, the real work begins. You must use averted vision, a technique where you look slightly away from the target, allowing the more light-sensitive parts of your retina to detect the faint, circular haze. It is a test of perception, a staring contest with the void. In that moment when the galaxy's soft light finally registers in your vision, something profound happens. You are no longer just learning about a collision that happened 3 billion years ago. You are witnessing its aftermath with your own eyes. You are gathering photons that have traveled across the cosmos for hundreds of millions of years, light from a ring of stars born from a cataclysm. That faint smudge connects you directly to the vast, dynamic, and often violent story of our universe, making an epic theory a tangible part of your own experience under the stars. The first clear window into this cosmic mystery was opened by the Hubble Space Telescope. For decades, Hoag's object was little more than a faint, enigmatic smudge on photographic plates, a ghostly hint of structure that fueled speculation but offered few answers. Hubble's position high above Earth's shimmering atmosphere changed everything. Freed from the blurring effects of our air, its sharp eye resolved the galaxy's form with stunning clarity. Suddenly, we could see the crisp separation between the golden core and the azure ring, the dark void between them, and the delicate, almost unreal perfection of the entire structure. This was not just an improvement in resolution, it was a transformation in understanding. Hubble's images turned an abstract astronomical curiosity into a tangible, detailed celestial object, a case study written in Starlight. The data it gathered went far beyond a beautiful picture. It allowed scientists to precisely measure the colors and brightness of the stars, confirming the vast age difference between the ancient core and the youthful ring. This was the crucial evidence that solidified the collision theory, moving it from a compelling idea to the leading explanation. Following Hubble's lead, a new generation of ground-based observatories joined the investigation. Equipped with advanced adaptive optics systems, these giant telescopes on mountaintops can now actively counteract the turbulence of the atmosphere. They use a brilliant trick, firing a laser beam into the upper air to create an artificial guide star, and then deforming their mirrors thousands of times a second to cancel out the twinkling. The result is a view from Earth that rivals the clarity of space, allowing astronomers to probe the galaxy's subtle internal motions. These technological marvels work in concert, each contributing a different piece of the puzzle. Hubble provided the definitive portrait, while adaptive optics telescopes on the ground dissect its kinematics, measuring the ring's outward expansion. Our entire modern narrative of a bullseye collision 3 billion years ago rests entirely on the data these instruments have provided. They are the tools that chiseled away the obscuring rock of distance and mystery, finally revealing the magnificent sculpture hidden within. Galactic smash-ups are actually the rule, not the exception. Our own Milky Way is a cosmic fossil record of such events, its history written in the stellar streams of galaxies it has long since consumed. Right now, we are on a collision course with the Andromeda Galaxy, a slow-motion car crash that will unfold over billions of years, but these common mergers are messy, chaotic affairs. They are galactic tangles that ultimately create huge, elliptical blobs of stars. The event that forged Hoag's object was something entirely different, a cosmic interaction of surgical precision. For a perfect ring to emerge, the universe had to line up a perfect shot. The target needed to be a stable, disc-shaped galaxy, like a spinning dartboard. The projectile had to be a smaller galaxy, dense enough to deliver a punch but not so large as to utterly shatter the disk. And most critically, the angle of attack had to be nearly perpendicular, a dead center bullseye. If the intruder came in at a shallow angle, it would tear the galaxy apart into a messy tidal tail. If it were too large, the two would simply merge into a shapeless cloud. This perfect alignment of mass, form, and trajectory is incredibly rare. This is why Hoag-type ring galaxies are such uncommon jewels in the cosmic tapestry. They are not the result of a common brawl, but of a single, perfectly thrown punch. So when you look at Hoag's object, you are not just seeing a galaxy. You are witnessing a cosmic lottery win, a moment of near-impossible alignment that transformed chaos into a perfect, enduring form. But even this perfect cosmic sculpture is not meant to last forever. The brilliant blue ring of Hoag's object is a temporary phase, a fleeting moment of beauty in a life cycle that spans tens of billions of years. The very process that gives it life also seals its fate. Those massive, luminous blue stars are furiously burning through their hydrogen fuel. They live fast and die young, exploding as spectacular supernova within a few 100 million years. Each explosion scours the surrounding space, blasting away the remaining gas and dust, the very raw materials needed to make the next generation of stars. Slowly but surely, the ring will use up its fuel. The firestorm of star formation will sputter and cease. The brilliant blue giants will vanish, and the ring will fade, dimming to a dull red glow as only smaller, longer-lived stars remain. Without new stars to replenish its light, the ring's glorious structure will begin to lose its definition. Over billions of years, the galaxy's own gravity and the subtle gravitational nudges from passing galaxies will work to erase this perfect form. The stars in the ring will slowly drift, their orderly expansion dissolving into a more chaotic, relaxed distribution. The galaxy's future may be to become a lenticular galaxy, a featureless disk without spiral arms, or perhaps even a quiet elliptical galaxy, a smooth swarm of ancient stars. And what of the Intruder, the artist that carved this masterpiece? If it survived the encounter, it is now a ghost receding ever farther into the intergalactic void. Its path is solitary, a silent witness to the beautiful, temporary structure it left behind. This cosmic story, from violent impact to serene ring to eventual fade, reminds us that even the most dramatic events are just single chapters. Galaxies, like stars, have life cycles, and we are privileged to witness this one in its most spectacular, though fleeting, stage. One of the most persistent myths about galaxies like this is the idea that the ring and the core are separate entities. It is easy to see why this misconception takes hold. The two components appear completely disconnected, a brilliant halo floating freely around a central island. But they are not two galaxies that happen to share the same space. They are the fractured pieces of a single, original galaxy. The entire structure, from the ancient yellow heart to the youthful blue ring, is bound together by the immense, invisible gravity of its dark matter halo. This single, cohesive system is the direct result of one transformative event, a bullseye collision that rearranged the galaxy's visible parts without tearing its underlying gravitational body apart. Seeing them as separate is like looking at the ripples on a pond and the stone that caused them as two unconnected objects, when in truth, they are different manifestations of the same single action. Another common misunderstanding paints these galactic collisions as purely destructive forces. The language we use often reinforces this. We talk about cosmic crashes, violent impacts, and celestial accidents. While the event is undoubtedly disruptive, it is fundamentally creative. The serene spiral that existed before was not annihilated, it was reborn. The Intruder galaxy did not simply smash a pre-existing structure, it triggered a firestorm of new star birth, illuminating the darkness with billions of new suns. This is not a story of pure destruction, but one of cosmic recycling on the grandest scale. The old order of the galactic disk was shattered, but from that chaos emerged a new, breathtakingly beautiful form. The ring of Hoag's object is a stellar phoenix, a testament to the universe's ability to forge new life from the rubble of the old. Clarifying these points is more than just scientific nitpicking. It refines our entire cosmic perspective. Understanding what ring galaxies are not, that they are not multiple objects and not merely scenes of destruction, is just as important as understanding what they are, single galaxies undergoing a profound and creative transformation. This shift in perception allows us to see the universe not as a static museum, but as a dynamic workshop where even the most violent events can sculpt enduring beauty. These galactic collisions are more than just cosmic spectacles, they are fundamental engines of change. The violent encounter that sculpted Hoag's object offers a rare and pristine window into the forces that shape all galaxies. By studying this perfect ring, we are essentially conducting an experiment on a cosmic scale, using the universe itself as a natural laboratory. we can observe the direct consequences of a specific type of impact, testing our theories of gravity, star formation, and galactic structure against a real-world example. This single, beautiful anomaly provides a controlled case study, a benchmark against which we can measure our understanding of how galaxies live and evolve. Without these extreme events, our view of galactic life would be dangerously incomplete, limited to galaxies in isolation. It is through these interactions that we see the most dramatic processes of growth and transformation in action. The calm, stately spiral that existed before the collision was a product of slow, internal evolution. The ring galaxy we see today is a product of a sudden, external shock, a rapid and violent rewriting of its destiny. This duality is crucial. It reveals that a galaxy's form is not predetermined, but is a dynamic balance between its internal clock and the chaotic environment it inhabits. Every smash-up, every near miss, and every direct hit leaves a mark, contributing to the incredible diversity of shapes we see when we look deep into the universe. The knowledge we gain from Hoag's object directly illuminates the past and future of our own celestial home. Our Milky Way is not an isolated island. It has a history of consuming smaller galaxies, and it is on an inescapable collision course with the Andromeda Galaxy. The serene spiral we see today is a temporary phase. Billions of years from now, the same forces that created Hoag's ring will reshape our entire sky. While our future merger with Andromeda will likely be messier, lacking the perfect bullseye precision, the underlying physics are the same. The same gravitational shocks will ripple through our galactic disk, compressing gas clouds and triggering firestorms of new star birth. The same invisible halos of dark matter will guide the chaotic dance. Studying Hoag's object lets us peer into that future, transforming an abstract prediction into a tangible, visualized outcome. This connection turns a distant curiosity into something deeply personal. It grounds a billion-year-old event in a narrative that includes us, linking the fate of a far-off ring of stars to the ultimate destiny of our own sun and its planets. The lessons learned from this one cosmic crescent are therefore universal. They are essential pieces in the grand puzzle of how structure emerges in our universe, from the serene beauty of a spiral to the perfect geometry of a ring, all connected by the invisible, creative hand of cosmic violence. That perfect ring of stars has transcended its role as a scientific specimen to become an icon. Its image now resonates far beyond the pages of astrophysical journals, finding a home in the human imagination. Artists and science fiction writers have been particularly captivated by Hoag's object, seeing in its symmetry a symbol of cosmic order and profound mystery. It appears as a backdrop in digital art, a mysterious destination in novels, and a visual metaphor for an advanced, harmonious universe. This is more than just aesthetic appreciation, it is a cultural bridge. The galaxy's form provides a rare point of connection between the hard, quantitative data of astronomy and the intuitive, emotional realm of human creativity. For a scientist, the ring is a density wave fossil. For an artist, it is a celestial mandala. Both perspectives are true, and both are essential to grasping its full significance. The public's embrace of this galaxy reveals a deep-seated need to find not just answers in the cosmos, but also meaning and beauty. Its influence shows that a single astronomical image can ripple through our culture, sparking wonder and inspiration in minds that may never understand the physics of a collisional density wave. This cultural journey underscores a profound truth about our relationship with the universe. The drive to explore is fueled as much by a search for beauty as it is by a quest for knowledge. Hoag's object, a structure born from violence, now stands as a quiet testament to that beautiful, inseparable union. every satisfying answer seems to raise a new and more intricate question. While the Bullseye collision theory elegantly explains the ring's existence, it leaves behind a trail of profound mysteries that continue to challenge astronomers. The most glaring unknown is the intruder itself. Is that faint, nearby galaxy truly the culprit, or is it merely an innocent bystander? If it is the one, its current state tells us very little about its original form or its precise trajectory billions of years ago. If it is not, then the real architect of this cosmic sculpture has vanished completely, leaving behind a perfect crime scene. The long-term stability of the ring is another puzzle. Our simulations show it can last for billions of years, but what subtle forces are at work, slowly changing its shape? Is the ring perfectly circular, or do our telescopes simply lack the resolution to see tiny, faint kinks and asymmetries? Then there is the ring's detailed chemical makeup. When astronomers analyze its light, they are reading the elemental fingerprint of the stars. Are the proportions of heavy elements like oxygen, carbon, and iron exactly what we would expect from a single wave of star formation, or do they hint at a more complex history? Could there be a second, much fainter ring further out, a ghostly echo from an even older collision that we have not yet detected? These are not minor details, they are fundamental to confirming or rewriting the entire story. Each unanswered question is a target for the next generation of observatories. The James Webb Space Telescope, with its infrared eyes, can peer through dust to analyze the ring's chemistry in unprecedented detail. Giant ground-based telescopes with extreme adaptive optics will map the motions of individual star clusters within the ring, searching for any subtle wobbles that might reveal the gravitational pull of the intruder's dark matter halo, even if its stars are long gone. This is how science truly operates, not as a search for final answers, but as an endless, thrilling conversation with the universe. The story of Hoag's object remains gloriously unfinished, its final chapters waiting to be written by the light of future discoveries. The search for cosmic mysteries like Hoag's object is no longer confined to professional observatories. Online platforms such as Galaxies have thrown open the doors of discovery, inviting the public to help sift through the millions of galaxies captured by automated sky surveys. Anyone with an internet connection can suddenly find themselves scrolling through images of distant universes, tasked with identifying strange shapes and peculiar structures. It is within this vast digital crowd that the hunt for other Hoag-like objects truly thrives. The human brain possesses an unparalleled ability to recognize patterns and spot anomalies, something computers still struggle with. A volunteer might be the first person in history to lay eyes on another perfect ring, another cosmic bullseye hidden in the data. This is citizen science in action, a global collaboration that turns curious observers into active participants in the exploration of our universe. Beyond the digital realm, amateur astronomers with their own backyard telescopes contribute in a different, equally vital way. Their long-term monitoring and high-quality imaging provide a continuous watch on the sky, capturing subtle changes in brightness or rare events that massive professional scopes, booked for specific targets, might easily miss. This partnership between professionals and amateurs creates a powerful synergy. The professionals provide the deep data and the theoretical framework, while the army of citizen scientists offers the processing power of human curiosity and the relentless coverage of countless dedicated eyes. This collaborative effort does more than just accelerate the pace of discovery. It fundamentally changes our relationship with the cosmos. It democratizes science, making the wonder of exploration accessible to everyone. The story of a galaxy like Hoag's object is no longer just a tale for astrophysicists. It is a narrative that we can all help to write, one observation at a time. This shared endeavor reminds us that science is not a remote, ivory tower pursuit, but a collective human journey driven by our innate desire to look up and understand the stars. The next chapter of this cosmic mystery will be written by a new generation of eyes on the sky. Upcoming space observatories, armed with revolutionary technology, are poised to dissect Hoag's object with a clarity we have only dreamed of. The James Webb Space Telescope, with its profound sensitivity to infrared light, will act like a cosmic X-ray machine. It will pierce straight through any lingering veils of dust within the ring, revealing the true heart of its star-forming regions. We will see not just the brilliant blue giants, but the faint, newborn stars still shrouded in their natal cocoons, allowing us to measure the exact rate and history of starbirth triggered by the ancient collision. This is like moving from a blurry photograph of a crowd to a high-resolution image where you can see every single face. Alongside Webb, the Nancy Grace Roman Space Telescope will contribute in a different but equally vital way. Its incredibly wide field of view is like switching from a telephoto lens to a grand panoramic camera. It will systematically scan vast stretches of the cosmos, not just studying Hoag's object in detail, but hunting for its long-lost relatives. Finding dozens or even hundreds of other ring galaxies will transform this single day to point into a rich statistical sample. We will finally understand how common these perfect bullseye collisions are and what subtle variations in their appearance can tell us about the precise conditions of the impact. These future missions will subject our theories to the most rigorous test imaginable, new and sharper data. They will probe the chemical composition of the ring, searching for the elemental fingerprints that trace the gas's origin. They might even detect the faint, ghostly glow of the Intruder galaxy's stripped-away stars, or the subtle gravitational distortions of its dark matter halo. The story of Hoag's object, a puzzle born from a single photographic plate in 1950, is far from over. Its deepest secrets are waiting for the light gathered by these new telescopes to finally be revealed. Hoag's object is not the universe's only celestial crescent. Astronomers have slowly assembled a small but significant family of similar galaxies, each one a cosmic cousin with its own unique twist on the perfect ring. Take letter 100,074, a distant island of stars that mirrors the classic Hoag-type structure. It displays that same stunning separation between a bright central core and a luminous outer ring, a clear signature of a similar violent past. Then there is SDSSJ 15171 plus 2135116.8, a galaxy whose name is a catalog number but whose form is pure poetry. It too boasts a detached ring, yet its colors and subtle asymmetries suggest a slightly different story, perhaps a collision with a different type of intruder or from a slightly different angle. These are not mere copies, they are variations on a theme. By comparing them, scientists can ask deeper questions. Does the width of the ring tell us about the speed of the intruder? Do the specific colors of the stars reveal the chemical composition of the original galaxy? Each new member of this exclusive club provides another data point, transforming a single mystery into a comparative science. The very existence of this small family is profoundly important. It confirms that the bullseye collision is not a one in a trillion fluke, but a reproducible, though rare, natural process. Our universe has a recipe for creating these perfect rings, and we are finally beginning to learn its ingredients. Every new Hoag-type galaxy discovered is another confirmation that we are on the right track, piecing together the conditions that can turn a chaotic impact into a work of enduring cosmic art. This perfect cosmic ring forces us to confront a fundamental duality shaping our universe. Is Hoag's object a magnificent fluke, a one-in-a-billion accident of trajectory and timing, or is it an inevitable, if rare, expression of the universe's own physical laws? Its existence speaks to a cosmos governed by two powerful forces. On one hand, we have the rigid, predictable rules of physics, the mathematics of gravity and motion that dictated exactly how the ring would form once the collision occurred. These laws are the universe's unwavering constitution, the non-negotiable framework within which everything must operate. On the other hand, we have the sheer, unadulterated chaos of initial conditions. The specific path of that intruder galaxy was not written in the stars. It was the product of billions of years of gravitational nudges, a random walk through the cosmos that just happened to line up for a perfect bullseye. This galaxy exists precisely at the intersection of these two realms, where absolute law meets sheer luck. It is a testament to a universe that is not merely orderly, nor purely random, but one that uses randomness as a raw material, sculpting it with physical law to create structures of breathtaking specificity. This balance is not unique to galaxies. Consider the evolution of life on Earth, where the immutable laws of chemistry and genetics provide the rulebook, but random genetic mutations and environmental shifts provide the creative spark. Or think of a single snowflake, its six-fold symmetry dictated by the laws of crystallography, while its intricate, unique pattern is shaped by the chaotic temperature and humidity fluctuations it encountered during its fall. Hoag's object is the galactic equivalent of that snowflake, a unique masterpiece born from the marriage of necessity and chance. So where does that leave us? We live in a cosmos that is predictable enough for us to comprehend its laws, yet unpredictable enough to constantly surprise us with its creativity. This beautiful, lonely ring challenges our desire for a simple narrative, insisting that the universe's most stunning creations often arise from this very tension. It suggests that our own existence on a pale blue dot orbiting a typical star might also be a product of this profound and fruitful interplay, a rare but not impossible outcome in a cosmos that is both lawful and wild. The force that carved this celestial crescent was local, but its roots stretch across the cosmos. This single violent encounter is a direct consequence of the universe's grand architecture, the vast cosmic web of dark matter and galaxies. Within this web, galaxies are not scattered randomly like sand on a floor. They are strung along invisible filaments, drawn into massive clusters and connected by long, lonely bridges of empty space. It is within these sprawling urban centers of the cosmos, these galactic superclusters, that encounters like the one that formed Hoag's object become possible. The dark matter halo that guided the intruder's perfect shot is itself a product of this large-scale structure, a knot in the universal fabric that drew both galaxies together over billions of years. So when we study the precise angle of that ancient collision, we are indirectly measuring the gravitational forces of the entire cosmic neighborhood as it existed eons ago. This local mystery is a single thread pulled from a much larger tapestry. Each ring galaxy we discover is a fossilized imprint of the cosmic environment in which it formed, a tiny probe of the universe's structure on the largest scales. Understanding why these collisions happen and how often helps cosmologists test their models of how the entire cosmic web evolved from the smooth soup of the Big Bang into the intricate filigree we see today. The story of Hoag's object is more than just the tale of two galaxies. It is a microcosm of the universe's dynamic and interconnected history, where a single, beautiful shape in the void whispers secrets about the architecture of everything. The tale of Hoag's object ultimately reveals a universe where chaos and beauty are not opposites but partners in creation. It is a story written in starlight, telling us that from a single, violent moment of impact, a structure of perfect symmetry can emerge and endure for eons. This journey through the evidence has traced the path from a forgotten collision to a celestial masterpiece, demonstrating how destruction can be a powerful engine for new life, and how the most rigid laws of physics can sculpt random chance into breathtaking order. The enduring mystery of this crescent moon galaxy humbles us, a clear sign that our cosmic maps still have vast, blank spaces marked only by possibility. Let this single, perfect ring inspire your own gaze upward. For every time you look at the night sky, remember that you are looking at a canvas of forgotten stories, each one waiting for a curious mind to bring its light back into memory. So keep wondering, keep questioning, and keep discovering. The next great cosmic secret might be hiding in plain sight, just waiting for you to see it.